Hello everyone. This video we can discuss about the properties of alpha, beta and gamma ray. Here have considered the properties like nature, charge, mass, range and natural sources. We know that the alpha ray, it is positive charged particles plus 2e charge, and it has natural isotopes, same as beta rays are negatively charged particles minus e, and the mass is 9.109 into 10 power minus 31 kilogram, and gamma rays are uncharged and it has no charge and no mass. Okay, while moving into the decay of radioactivity, the activity of a quantity of radionuclides is the number of nuclear transformations which occur in the quantity that unit time. Here, the decay constant, it is defined as del n by del t, it is equal to minus lambda n, where lambda is the decay constant for the radionuclide, n is the radioactive atoms of a certain radionuclide, and here the minus sign, it indicates that del n by del t, it is negative, that is n is decreasing with time. Okay, this shows the decay time versus the number of atoms. Here the number decaying during time interval is represented here. Here this number 908.0729656 and 590, the number remaining after time interval. Okay, here the some radionuclides can undergo more than one type of radioactive decay, and also the total decay constant for the radionuclide is the sum of the branching decay constants like lambda equal to lambda 1 plus lambda 2 plus lambda 3 plus etc. It goes up to lambda n. Okay. While coming into exponential decay, the decay factor, the fraction of radioactive atoms remaining after a time t, it is called the decay factor df. It is represented by e power minus lambda t. Here we have n of t is equal to n of 0 e power minus lambda t, where n of t is the number of atoms remaining after a time t, it is equal to n of 0. The total number of atoms at time t is equal to 0 multiplied by the factor e power minus lambda t. Okay, here in previous lectures we talk about half-life, T1 by 2. Then what do you mean by half-life? It is the time required for a radionuclide to decay to 50% of its initial activity level. The half-life and decay constant of a radionuclide are related as T1 by 2 is equal to logarithmic, natural logarithmic of 2 by lambda, lambda equal to ln2, logarithmic 2, natural logarithmic 2 divided by T1 by 2, half-life. Here the average lifetime T of the atoms in a sample has a value that is characteristic of the nuclide, and it is related to the decay constant lambda. Here tau equal to 1 by lambda. Here the average lifetime of the atoms of a radionuclide is therefore longer than its half-life by a factor 1 by ln 2, it is more or less equal to 1.44. Here we have some methods for determining the decay factors. Here we have tables of decay factors. It is very essential that an individual working with radionuclides know how to determine decay factors. Perhaps the simplest and most straightforward approach, it is used to use the tables of decay factors which are available from the vendors of the radiopharmaceuticals, instrument manufacturers and so forth. The tables are generated easily with computer spreadsheet programs. Here we have some packet calculations, mini packet calculations, and calculators have the capabilities for calculating the exponential functions. And here this shows, the graph shows the radionuclide provided that the elapsed time t is expressed in terms of the number of radionuclide half-lives elapsed. Here an example of universal decay curve. It represents the decay factor with the number of half-lives elapsed. Here we have image frame decay corrections, and also we have specific activity. Here we have decay of a mixed radionuclide sample, and while talking about the specific activity of a radionuclide, it is a carrier-free specific activity, CFSA. This specific activity has units of becquerels per gram, and also it has some units. Thank you. This shows the decay of mixed radionuclide sample, and in the further videos we can discuss about the applications. Thank you.